For the first part of 4.4, our objective is to use the fundamental theorem of calculus to evaluate definite integrals. Let's start with derivative. What is derivative? What does it mean? Remember that derivative is another way to say the slope of the tangent line. So thinking of a graph, I'll give you a little example to look at. We can sketch something. We'll call this y equals f of x. And I'm going to pick a point somewhere on here, and I'm going to say to find the derivative of this, what I mean I'm finding is the slope of the line that's tangent at this point. So normally, to find slope, I need to have 2 points and do the change in y divided by the change in x. But to find the derivative, that's dy dx. That's the exact slope at that point. Let's take a moment and talk about what is area. Lately, we've been talking about area. Let's just look at a graph. And I'm going to try to draw a similar function to what I drew on the left. And again, I'm going to call this y equals f of x. And I'm going to mark off from one x value, we'll call it a, to another x value b. And when we've been talking about area, we've been saying the area between the function and the x-axis from some x value to another x value. So I'm going to shade in that area so we can get an idea for what we're talking about. And we've said, well, we can't find that exact area. Of course, we've used a limit process, but we started the limit process by saying, let's estimate a rectangle that does a little bit of underestimating and a little bit of overestimating, and we can find the area of this rectangle. Well, how do we find the area of this rectangle? Well, we do the width times the length, or times the height. What's the height of it? That's the change from this y-coordinate to this y-coordinate, so that's the change in y. And what's the width of it? Well, that's from this x-coordinate to this x-coordinate, so that's the change in x. So area, this area that we're looking at here, is approximately the change in x times the change in y, its length times its height. So notice these two scenarios side by side. We've done a lot with derivatives, the slope of the tangent line, and it looks like dy over dx, or the change in y over the change in x, versus when we did area, which is the change in y times the change in x. Notice how they are inverse processes of each other. In the slope, we are dividing change in y and change in x, and in area, we are multiplying change in y and change in x. Dividing and multiplying are inverse processes. So what else does this tell us? That tells us that the derivative and the, well, what's the inverse process of the derivative? That's right, the antiderivative. So whereas slope is the derivative, the inverse process of it is the antiderivative. So now we start to make some connections. If you remember in the previous section, we started talking about definite integrals. Well, a definite integral comes from an integral, and remember the synonym for antiderivative was indefinite integral, so that was that integral symbol, the integral of some function with respect to x perhaps. Well, the definite integral is when we just put those limits in there. So the derivative, or the slope, change in y divided by change in x, is the inverse process of the antiderivative, or the area, change in y times change in x. So now we see that the antiderivative is helping us to find the definite integral. And this is basically the fundamental theorem of calculus. So the fundamental theorem of calculus tells us that if f is a continuous function on the closed interval a to b, and uppercase F is an antiderivative of f on that closed interval a to b, then the definite integral from a to b of f of x dx is the antiderivative evaluated at the upper limit b minus the antiderivative evaluated at the lower limit a. Remember that graphically, this means the net area bound by the function f of x, in this case, and the x-axis over the interval a to b. Let's apply this fundamental theorem of calculus. Evaluate the following integrals using the fundamental theorem of calculus. Remember, there are other ways to do it, but we are going to use the fundamental theorem of calculus, meaning the antiderivative. So we have the definite integral from 0 to 1 of x cubed plus 2 dx. First, we're going to take the antiderivative of each of these terms. Using our power rule, that makes x to the fourth divided by 4 plus 2x. And then the notation for writing this is we put a bracket with our limits, 0 at the bottom still, 1 at the top. We could use brackets on both sides if we wanted, but often you see it just on one side. This is our antiderivative. First, we evaluate the antiderivative at the upper limit, b. The upper limit is 1. So first we will plug in 1. 1 to the fourth over 4 plus 2 times 1. That's plugging in the upper limit. Then we will subtract and plug in the lower limit. The lower limit is 0. So 0 to the fourth over 4 plus 2 times 0. We'll evaluate each of these. This one makes 1/4 plus 2 minus this one makes 0, and altogether we get 2 1/4 or 17/4, and that's using the fundamental theorem of calculus. Let's take a look at another one. Notice the asterisk, meaning this problem is taken from an AP exam. Now, keep in mind, when we have a quotient or a product, we are not ready to take antiderivatives. Make yourself a note about that. Cannot take antiderivatives from a quotient, which is what we have here, x is in the denominator, or a product. So first, we have to make it not a quotient. So let's rewrite this definite integral. Integral from 1 to 2, x divided by x cubed minus 4 divided by x cubed dx, and that will turn into the integral from 1 to 2, 1 minus 3, negative 2, minus 0 minus 3, negative 3. There is our new definite integral. Now we have no quotient or no product. We can use our power rule. The antiderivative of x to the negative 2, when we add 1 to the exponent, we get x to the negative 1 divided by negative 1 minus, add 1 to the exponent, 4x to the negative 2 divided by negative 2. Put our brackets to show we have limits to plug in, 1 to 2. Now, before I plug in the limits, I rewrite so I don't have any negative exponents. So this will put my x to the first in the denominator, negative 1 over x, negative 4 divided by negative 2, so plus 2 over x squared, and then my brackets to show I still have limits to plug in. Remember, we first plug in the upper limit, the number at the top. No matter what it is, the number at the top. So this turns into -1 over, I'm plugging in 2, plus 2 over 2 squared, minus, using parentheses because I've got a lot of stuff there that I'm subtracting with a lot more stuff, plugging in the lower limit now, 1 and 2 over 1 squared. We simplify that and get -1. See how the fundamental theorem of calculus is used? Let's take a look at this different kind of example, again pulled from an AP exam. If the definite integral from -2 to 2 of x to the 7th plus k dx equals 16, then k equals what? Well, k we're reading as a constant. So when I take the antiderivative of that, I'm going to treat it like I would if it were a 5 or a 3 or any other constant. Let's go ahead and take the antiderivative of this using the fundamental theorem of calculus. Now, another idea is I notice that this term in the function is odd. And when I have an odd function and the limits go from numbers that are equidistant from the origin, remember that that creates equal area above and below the x-axis. So if I think of this as two separate integrals, the integral from -2 to 2 of x to the 7th dx plus the integral from -2 to 2 of k dx, then using the shortcut that this net area will be 0, the net area will be 0, I really only have to do this antiderivative. So this antiderivative is the constant times x, of course with the brackets, because I still have the limits -2 to 2. Now remember, they said equals 16. So I'm going to write equals 16 so I don't forget I still have that part. I plug in the upper limit first, so k times 2 minus, and then the lower limit, k times -2, still equals 16. K times 2 is 2k. That makes plus 2k. 4k equals 16, so k equals 4. Not too bad. Let's visit one more example. The integral from -4 to 1 of the absolute value of x squared minus 9 dx. Now, just like when I have a product or a quotient, I cannot take the antiderivative while I have absolute value symbols. Let's make a note of that. Cannot take the antiderivative or the derivative, by the way, as we know, with absolute value symbols present. We just can't do it. Now really, the absolute value symbols are there as a shortcut of a piecewise function. Let's talk about that for a moment. If we were to just look at the graph, y equals x squared minus 9, forget about the absolute value symbols for a moment. That would look like a parabola whose graph is shifted down 9 units, so the vertex is at -9, and it goes through the x-intercepts of +3 and -3. Now, how do I know it goes through those x-intercepts? Well, remind ourselves of some algebra. If x squared minus 9 equals 0, that means x could equal positive or -3, whether we factor or solve to get the x by itself. Now, if I add the absolute value symbols in there, what that means is we're going to make anything that's negative or below the x-axis turn positive or go above the x-axis. So it would look like this. So really, this function is equal to the piecewise function, where the normal, the regular part of the graph, which was just x squared minus 9 as it was to begin with, is good for the part of the domain where x is less than -3 and where x is greater than 3. And then the part that we had to flip over, so the negative of the x squared minus 9 graph, is what we had to do between -3 and 3. So it's really those two pieces that we're looking at. Now we could have equals with either this set or this set. So I'm just going to stick them in here to be a complete function. So what we need to do is evaluate from -4 to 1 of the pieces of the function. So notice, because we're going from -4 up to 1, then I need to include this piece of the function, so -4, and then up to 1, and then a part of this piece of the function, because the 1 is between -3 and 3. So I'm going to need to make two integrals because I'm using two different expressions, kind of two different functions. So I'm going to start with the integral from -4 up to where this domain ends, -3. And that's of that expression included in that constraint, x squared minus 9 dx. I'll add that to the integral of the other function, the negative of x squared minus 9. I'll pick up where I left off at -3 and we'll end at 1. That's the region that's in this interval. And now it's like I have two integrals to solve. So let's go ahead and do each one. First, the antiderivative for this one, x cubed over 3 minus 9x. This one goes -4 to -3. I could finish this, or to not forget that I have this other piece, just continued with the antiderivative portion. So this will be the negative of x cubed over 3 minus 9x, and this one goes -3 to 1. Be very careful when we have multiple integrals that we're doing at once. This one, the top limit going in first, -3 cubed over 3 minus 9 times -3. That's the first number plugged in, minus, and now -4, the lower limit plugged in, -4 cubed over 3 minus 9 times -4. Now, that's only that first section. This part right here is this part right here, and now we still have to do this part. So for this part right here, we'll say plus, and now I plug in the upper limit from that section, the negative of 1 cubed over 3 minus 9 times 1, minus, now the lower limit, the negative, I'll change that to a plus because it's minus the negative, of -3 cubed over 3 minus 9 times -3. All of that part. And then we can simplify. And simplifying in the end gives us 30 if we need to simplify. Thanks for watching.